After we have done designing the reinforcement bar for the slab, undertaking bending moment, our next step it will be checking the shear resistance of the slab. To do so, we will need to first determine the shear loads acting onto the slab. Refers to table 3.15. In British Standard Act 110, the table is used to determine the shear coefficients, and the shear coefficients is used in the equations 19 and 20 to determine the shear loads acting onto the slab. To determine the shear coefficient, you need to first know the classifications of the panel. We are designing the slab BC12 based on the dimensions given. These are two discontinuous edges, and the discontinuous edges are at the shorter span. With that, we know that it is two short edges discontinuous. Refers to table 3.15. Two short edges discontinuous. There are a series of coefficients. The coefficients is determined on basis of the Ly per Lx ratio. With that, you will need to get the Ly divided by Lx. That gives you a ratio of 1.4. That means 1.4 ratio, two short edges discontinuous. The shear coefficients, it will be 0.48 and 0.26. The 0.48 is for the shorter span, which is referring to the continuous edge. That means the shear loads appears here. Whereas the 0.26 is referring to the longer span, and it appears at the discontinuous edges. That means it appears here. Now, how do you define which edge is shorter span and which edge is longer span? When we talk about the shorter span, we are referring to the cut sections of the slab. When you cut the sections and view from the side, you will see the shear force diagram something like this. As for the longer span, you cut these sections and then draw the shear force diagram. It will appear something like this. So the coefficients given here represent the shear force on that particular section. Among the two ratio of them, obviously this is bigger. That means the shear loads acting on the continuous edge is relatively larger. For simplicity, you may use the largest shear load acting on the slab. Check the resistance. If the resistance is adequate, that means the other smaller value will also be passed. With that, we will use the bigger shear coefficients for us to calculate the shear load. Use the equations given in the British Standard. The shear coefficients is 0.48. The Lx refers to the shorter span, which is 4 meter, and the N here refers to the design load. The design for the shear resistance is at the ultimate limit state. Therefore, the design load should be 1.35 GK plus 1.5 QK, which we have calculated it previously. It is equals to 9.96 kN per meter square. Substitute the relevant value into the equation. You get the shear loads 19.1 kN. With that, the 19.1 kN shall be used to check the shear resistance. Now, to check for the shear resistance, or more specifically, we are talking about the equations used to design the shear. There are two types. These are the first group of equations to be used. This is another group of shear equations to be used. The question here is which equation should be used. To make it simple, these equations are meant for beam elements. The cross-sectional area is relatively low as compared to the shear load. This will lead to a situation that the shear resistance by the concrete alone is insufficient to take the shear load. And when this happens, you require shear reinforcement. To calculate the shear reinforcement, you will need to first determine the shear angle and then design the shear reinforcement accordingly. However, in the case that the cross-sectional area of the concrete is relatively large as compared to the shear load, where the concrete alone is sufficient to undertake the shear loads without requiring additional shear reinforcement, then you may use this set of equations. These are the equations used to check whether the shear resistance of the concrete is sufficient. As long as you confirm that the shear resistance is sufficient, that means no shear reinforcement shall be required. In other words, these equations are not meant to design the shear reinforcement. They are used to determine whether the shear reinforcement is required. Now, these are the conditions where the shear reinforcements are required and not required. To make it simple, if you are talking about large elements such as slab, footing, staircase, and etc., relative to the shear loads acting onto the member, the sections is relatively large. Most likely shear reinforcement shall not be required. Therefore, you will use this set of equations to check. As for small members such as beams, then you use this set of equations. Coming back to this example, we are designing a slab, and you know that the slab are basically large panel. The shear loads is not quite high, which based on the calculations it is only 19.1 kN. Most likely the shear resistance shall be sufficient and no shear reinforcement shall be required. With that, you may use this set of equations to check. There are two equations here. VRDC represents the shear resistance of the concrete, taking into considerations of the amount of reinforcement bar provided, whereas VRDC minimum represents the minimum resistance of the concrete, without taking account the amount of reinforcement bar provided. In order to use these equations, you will need to first determine the K and the raw one. That's why we calculate this K first. The K is in the functions of the effective depth. This we have calculated earlier on, which is equals to 115. Substitute it into the equations, you get K equals to 2.32. It is greater than 2.0. The equation tells us that the K should not be more than 2.0. Therefore, we will just use the K equals to 2.0. Next is to determine the percentage of reinforcement bar. You need to get the AS first. This AS represents the area of reinforcement bar provided, which based on the calculations, it will be equals to 224 mm square. The AS here is not the amount of reinforcement bar required, as the purpose of having this row 1 here is to provide the informations regarding the amount of reinforcement bar provided in the slab in order to determine the shear resistance. Therefore, you may use the exact amount of reinforcement bar in the slab instead of the amount of reinforcement bar required. The B here represents 1000 mm, as the slab is designed on the basis of 1 meter unit width. As for the D here is equals to 115. Substitute the value, you get 0.0017. The row 1 here cannot be more than 0.02. In other words, if the amount of reinforcement is more than 2% of its cross-sectional area, we will assume that the amount of reinforcement equals to 2% only. The excess of the reinforcement will be assumed not contributing to the shear resistance. For a typical slab, when the loops are relatively small, you will not expect your reinforcement to be heavily reinforced in the slab. Therefore, under normal circumstances, the row node will not be greater than 0.02. Now, if you encounter in your calculations, when your row node is more than 0.02, you might need to recheck your calculations. It is unless your slab is heavily reinforced. Otherwise, the ratio will not be more than 0.02. Since the calculated ratio here is 0.017, less than the 0.02, then you will use it in the equation. Next step, it will be substituting the values into the equations. The FCK is given in the questions, which is 30 Newton per mm square. Substitute all the value into the equations, you get the shear resistance of the concrete, considering the amount of reinforcement bar provided, 44.7 kN. Next, you find the VRDC mean, which represents the shear resistance of the concrete alone. Substitute the equations. 56.9 kN is obtained. Now the shear resistance, it will be governed by the greater value of the two. Since VRDC mean is greater than VRDC, your shear resistance of the slab, it will be 56.9 kN. And your shear resistance is checked against the shear load, which is 19.1. It is greater than the shear load. That means the shear resistance is adequate. No shear reinforcement shall be required.